Our universe is a vast and mysterious place. We see stars, planets, and galaxies, but what we see is only a small part of the story. Astronomers have discovered something strange. There's a hidden force at play. It's powerful and invisible. We call it dark matter. Dark matter doesn't emit light, it doesn't reflect light either. We can't see it directly, so how do we know it's there? The answer lies in its gravity. Dark matter's gravity affects the way galaxies move and behave. It's a cosmic mystery that has intrigued scientists for decades. The quest to understand dark matter is a journey into the unknown. Dark matter is a mysterious substance that makes up a large portion of the universe. Despite its name, dark matter isn't just a shadowy counterpart to the matter we know. It's a fundamental component of the cosmos, yet it remains one of the greatest enigmas in modern physics. Scientists estimate that dark matter constitutes about 27% of the universe's total mass and energy. This is a staggering amount when you consider that the matter we are familiar with, the stars, planets, and everything on Earth, only makes up about 5% of the universe. It's different from the matter we know. The matter we interact with daily is made up of atoms, which consist of protons, neutrons, and electrons. These particles form the building blocks of everything we see around us. However, dark matter doesn't fit into this familiar framework. It doesn't emit, absorb, or reflect light, making it completely invisible and detectable only through its gravitational effects. The matter we see is made of atoms. These atoms combine to form molecules, which in turn make up the various substances and materials we encounter. From the air we breathe to the food we eat, everything is composed of these atomic structures. But dark matter is fundamentally different. It doesn't interact with electromagnetic forces, which means it doesn't form atoms or molecules. Dark matter doesn't interact with light. This lack of interaction with light is why we can't see it directly. Instead, we infer its presence through its gravitational influence on visible matter. For instance, when we observe the rotation of galaxies, we notice that the outer regions rotate much faster than they should if only visible matter were present. This discrepancy suggests the presence of an unseen mass, which we attribute to dark matter. That's why it's invisible to us. Despite being invisible, dark matter plays a crucial role in the structure and evolution of the universe. It acts as a cosmic scaffold, providing the necessary gravitational pull to hold galaxies and clusters of galaxies together. Without dark matter, the universe as we know it would be a very different place, but we know it's there because of its gravitational effects. One of the most compelling pieces of evidence for dark matter comes from the phenomenon known as gravitational lensing. This occurs when the gravitational field of a massive object, like a galaxy cluster, bends the light from objects behind it. The amount of bending can be used to estimate the mass of the foreground object, and often the mass inferred is much greater than what we can see, indicating the presence of dark matter. Imagine a bowling ball on a trampoline. This is a common analogy used to explain how gravity works. The bowling ball represents a massive object like a star or planet, and the trampoline represents the fabric of space-time. The ball creates a dip in the trampoline's surface. This dip represents the warping of space-time caused by the object's mass. Smaller objects placed on the trampoline will roll towards the bowling ball, just as smaller masses in space are attracted to larger ones due to gravity. This is similar to how gravity works. Massive objects like stars and planets warp the fabric of space-time, creating a gravitational pull that attracts other objects. Dark matter, although invisible, also contributes to this warping effect. Massive objects like stars and galaxies warp the fabric of space-time. This warping is what we perceive as gravity. The more massive the object, the greater the warping and the stronger the gravitational pull. Dark matter's gravity adds to this warping. Even though we can't see dark matter, its gravitational influence is undeniable. It helps to explain the motion of galaxies and the large-scale structure of the universe. It affects the movement of stars within galaxies. Observations show that stars in the outer regions of galaxies move faster than expected, suggesting the presence of an unseen mass providing additional gravitational pull. It also influences how galaxies cluster together. Dark matter's gravitational effects extend beyond individual galaxies, affecting the formation and distribution of galaxy clusters. These clusters are some of the largest structures in the universe, and their existence and behavior provide further evidence for the presence of dark matter. One of the key pieces of evidence for dark matter comes from the rotation of galaxies. When we observe these magnificent spiral structures, we notice something peculiar about the way their stars move. The stars in these galaxies don't behave as we would expect if only the visible matter were influencing their motion. Stars in spiral galaxies orbit the galactic center. This central region is densely packed with stars, gas, and dust, creating a gravitational pull that keeps the stars in orbit. However, the way these stars orbit reveals a mystery that has puzzled astronomers for decades. Astronomers expected stars farther from the center to orbit slower. This expectation comes from our understanding of gravity and orbital mechanics, similar to how planets in our solar system behave. The farther a planet is from the sun, the slower it moves in its orbit. This is like planets in our solar system. For example, Mercury, which is closest to the sun, orbits much faster than Neptune, which is farthest away. This is because the gravitational pull weakens with distance, causing outer planets to move more slowly. But observations revealed something unexpected. When astronomers measured the rotation speeds of stars in spiral galaxies, they found that stars far from the center were moving just as fast as those near the center. This was a surprising discovery that defied the laws of gravity as we understood them. The stars on the outskirts of galaxies were moving much faster than predicted. According to the visible mass in these galaxies, the outer stars should have been moving more slowly. This discrepancy suggested that there was more to these galaxies than met the eye. This suggests that there's more mass in galaxies than we can see. The visible stars, gas, and dust couldn't account for the high speeds of the outer stars. There had to be an additional, unseen source of gravity influencing their motion. This unseen mass is attributed to dark matter. Dark matter doesn't emit, absorb, or reflect light, making it invisible to our telescopes. Yet its presence is inferred from its gravitational effects on visible matter. If galaxies only contained the matter we see, they would fly apart. The gravitational pull from the visible matter alone isn't strong enough to keep the stars bound in their orbits, especially at the outer edges of the galaxy. The visible matter doesn't have enough gravity to hold them together. Without an additional source of gravity, the stars would drift away, and the galaxy would lose its structure. Dark matter provides the extra gravity needed to keep galaxies intact. It acts as a cosmic glue, holding the stars in place and maintaining the galaxy's shape and stability. It acts like an invisible glue. This mysterious substance, though unseen, plays a crucial role in the structure and dynamics of galaxies, making it a fundamental component of our universe. Another compelling piece of evidence for dark matter comes from galaxy clusters. These colossal structures are not just a random collection of galaxies, they are bound together by the invisible force of gravity, creating some of the most massive and fascinating objects in the universe. Galaxy clusters are the largest structures in the universe held together by gravity. They contain thousands of galaxies, vast amounts of hot gas, and intriguingly, a significant amount of dark matter. This dark matter doesn't emit, absorb, or reflect light, making it invisible and detectable only through its gravitational effects. The Bullet Cluster is a prime example. Located about 3.7 billion light-years away from Earth, it has provided astronomers with a unique opportunity to study the effects of dark matter in a cosmic collision. It's the result of a collision between two galaxy clusters. This cosmic event, which occurred millions of years ago, has left behind a fascinating aftermath that continues to intrigue scientists. When these clusters collided, the hot gas they contained interacted and slowed down. This interaction caused the gas to emit X-rays, which can be observed with X-ray telescopes, providing a clear picture of the gas distribution in the cluster. However, observations using gravitational lensing revealed something astonishing. Gravitational lensing occurs when a massive object like a galaxy cluster bends the light from objects behind it, creating distorted and magnified images. This effect allows astronomers to map the mass distribution within the cluster. The majority of the mass in the Bullet Cluster was not concentrated where the hot gas was. Instead, the mass was found in regions that did not correspond to the visible matter, suggesting the presence of an unseen component. Instead, it was located in two separate regions. These regions were aligned with the positions of the galaxies, which had passed through each other during the collision, largely unaffected by the interaction that slowed down the hot gas. These regions correspond to where the galaxies from each cluster had passed through each other. The galaxies, being mostly empty space, did not interact much and continued on their paths, while the hot gas, which makes up the visible matter, was left behind. This separation of visible matter and gravitational mass provides strong evidence for the existence of dark matter. The gravitational lensing data showed that most of the mass in the bullet cluster was in the regions where the galaxies were, not where the hot gas was. This indicates that the majority of the mass is in the form of dark matter, which does not interact with the hot gas and is only detectable through its gravitational effects. Scientists continue to study the bullet cluster and other galaxy clusters to understand the nature of dark matter. These observations are crucial for unraveling the mysteries of the universe and understanding the fundamental components that make up the cosmos. The bullet cluster remains one of the most compelling pieces of evidence for dark matter, showcasing the invisible yet powerful force that shapes our universe. As we continue to explore and observe, we move closer to uncovering the secrets of dark matter and its role in the cosmic tapestry. Scientists have ruled out many familiar candidates for dark matter. It's not made of faint stars or black holes. These objects would emit some form of radiation. We haven't detected any such radiation coming from dark matter. It's also not made of ordinary matter like protons and neutrons. This type of matter interacts with light. Dark matter does not. So, if dark matter isn't made of anything we know, what is it? This question has puzzled scientists for decades.